Folks, welcome back to EarthSky. I'm Dave Adalian, and my guest today is Peter Jenniskens. He is a researcher at NASA, Search for Extraterrestrial Intelligence, SETI, and he is an expert on meteors and meteor showers. He led the first team to track a meteor all the way from its discovery in space right down here to planet Earth. Peter, welcome. Thank you for being here.
Thank you.
So today you're running another program also funded by NASA, and that one is called CAMS. It is the Cameras for All Meteor Surveillance. It's a network of linked cameras and computers, and it scans the entire night sky, or as much of it as you can with your network, every night. Started with a handful of cameras in the Bay Area and San Francisco. Tell us what exactly that is, and why did you create it? Why are we doing this? Tell me about that.
So we started CAMS some years ago with the purpose of mapping our meteor showers. I'd written a book on the dynamics of meteor showers, this one, which had a table in it that listed all the meteor showers that are active through the year. And at the time, there was only a handful of photographic data. There were, a lot of observations done by visual observers, laying back on a reclining lawn chair, looking at the sky, plotting meteor trails on maps. And that information had been used to understand what sort of meteor showers are there in the sky, when to go out, when satellites might be in danger from meteorite impacts, and so on. So meteor showers were studied for a very long time. But when I was trying to put a list together of, okay, which showers we really know about, it took forever. The literature was incredibly opaque, and the data was very difficult to interpret. It was very uncertain. And so then the idea came to try and do this with video cameras. And video cameras have improved over the years tremendously. At the time, the best camera out there was this WATEC low-light video camera. And so we basically built a system that had boxes of these pointed at different places in the sky. They would film the night sky. Every time when a shooting star would come by, it would record its trajectory against the stars. That would give us directions. And those directions, we would then triangulate it, determined how the meteor was moving in the atmosphere, and from that calculate what the orbit was just before hitting the Earth's atmosphere. And so we've done that now for since we first started in 2010, and we've gradually increased the network. In 2017, we added a lot of cameras in the southern hemisphere, and that made a big difference, because it allowed us to map the southern hemisphere showers. And all of that ultimately led to this, Atlas of Earth's Meteor Showers, my latest book. This is basically now a complete overview of what we know about what meteor showers are there each night.
And I'm going to put a link for people who want to pick up copies of your books in the description of this video. Speaking of the early days, here's a picture of, what are we looking at? Tell us what this is.
Well, the first place that allowed us to put a box of cameras for this type of work was Fremont Peak Observatory. And it's a very interesting amateur built and operated observatory. It has a 1-meter telescope, does public outreach programs in the summer months. And on the roof, next to the big telescope, we built our first box with cameras. And it was just at the right distance for, where I live in the San Francisco Bay Area, and from Lick Observatory. Lick Observatory was the second site where we set up a box. And that allowed us to then triangulate the meteor trajectories in the sky.
Okay. And so is that still the main goal of the project these days? Is that still what you're doing?
These days, we've shifted more towards not so much mapping out the showers we see every year, but mapping out the showers we do not see every year, the sort of the unusual things in the sky. And you'd be surprised. There is a lot of those going on. As a matter of fact, today we're taping this on, 16th of September, 2025. There is actually an outburst going on. There is a meteor shower in the sky that only shows up every 5 years or so, called the key cygnets. Very slow meteors radiating out of the constellation Cygnus, and last night they had their peak. Unfortunately, it's going to be the next couple of days, and then that activity will drop off very quickly, and then we have to again wait for another 5 years for this shower to show up again. But those are really interesting showers because they come from comets that are relatively recently let go of some dust. The dust is still together, still confined, and that's why we do not see these showers every year.
Okay, so now this project, it started with just a few cameras in the Bay Area. Now it's global. It's all over the place. Is this just for scientists, or is this a citizen scientist program? Can people get involved in this?
People can get involved. It is the CAMS project is very much set up as being concentrated in a few different locales spread over the world. So we have a sort of a full view of the night sky at all times. Mm-hmm. But around many of these networks, you can set up your own camera, and that can contribute to the data being collected.
Okay, and do you need a special kind of a camera, or these just, what kind of camera, what kind of equipment would somebody need if they wanted to get in?
For this type of work, a regular a Nest doorbell camera, something like that, is not sufficient. You need to have a camera that is set up to do the meteor detections that looks for these shooting stars in your video. And we have two different camera types at the moment. We still use the old Wattec analog camera. So if you still have those sitting in your cupboard, you can set those up immediately. We also have a modern 4K type of camera that one can use for a network of this sort.
Okay, so people might expect to see something like this. This was just shot a couple of days ago during that Aurora that Aurora display we had, but this is the kind of stuff that you're recording. It's well, can you tell us what this is?
Well, we'd wish to record this. This is actually done with a digital still camera at very high resolution. Very rare to get a fireball recorded with this much detail. This was a meteorite fall. This was a bright fireball that appeared in the sky back in 2012, I believe, where there was a meteorite fall in a town just north of San Francisco called Novato. Our cameras recorded the event. We calculated the trajectory, and we determined that the trajectory ran over the town of Novato. Put that in a newspaper, and a person in Novato, Lisa Weber, she read the story, thought it was very interesting, and she had heard a tock 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 sound on the roof of her house previous night, and she had gone out in the garage to look for raccoons and so on, but didn't see anything out of place and had forgotten about it. And she read our story and thought to have another look, and so she went outside, looked in the garden, didn't see anything, put a ladder up against the garage, went all the way to the roof, didn't see anything, but when she came down the ladder, she found this rock sitting there on the ground, and the rock was a little bit, out of place. So she sort of recognized it because the rock didn't have any dirt on it. It was sort of looked clean, and it was just sitting on top of the soil, and that's what caught her attention. And that turned out to be a real meteorite. And so these are some of those meteorites from Novato. You'll recognize them. Yeah, you'll recognize them because they are covered in a layer of glass, which we call the fusion crust. And so that's how you recognize a meteorite. You don't look at the inside, magnets, and nothing of that is conclusive, But if you see this layer of glass covering the surface, then that is something that's very unique to meteors. They go so quickly through the atmosphere, they melt, the melt is being blown away by the air, and then what lands on the ground is a rock with still a thin layer of this melt covering it. And so initially, this rock was the rock that Lisa found didn't have that fusion crust on it, or just a few bits of it. And so initially, I didn't quite recognize it as such. But then, in hindsight, it turned out that this particular meteorite was very shock blackened. It basically was glass already, so it didn't hold on to its glass. And other meteorites were found that clearly had this fusion crust.
Yeah, quite a few, it appears. Here's you and a group of folks at a meteorite event.
Exactly, yes. Lisa and some of the other people involved in the search, including Jason Utah's there on the right, who found one of the meteorites. It's very, very exciting to go look for meteorites. Once you know sort of in what area meteorites fall, you just walk around, you look left and right, and look for basically rocks that are out of place. Strange looking. There's no real good description you can give on what a meteorite looks like, because I've been fooled myself. We went looking for a meteorite that fell in Germany last year near the town of Ribbeck. That one was that fell from another asteroid that was seen coming in, and so the asteroid had been tracked. The trajectory was very well known. The winds were calculated. We knew where the strewn field was. We walked around. We were in the right place. Could not find it, and it turned out that it was an orbrite, and an orbrite looks like terrestrial rock from a distance. Only if you look at an orbrite. It's called an orbrite.
Orbrite.
Yeah. It's sometimes you can have rare meteorite types that are but again, once we'd seen one meteorite, it was very easy to find. Well, with our group, we had one within 2 hours. Once we knew what to look for.
Once you knew what to find, right?
So the first one is always the most difficult one to find.
And then they know what to look for, I think. Yeah, yes, exactly. So what are these discoveries, the meteor showers, putting these together with a parent comet or the parent body, it's not always a comet, what can that tell us about the nature of the solar system, of threats to Earth? I mean, why do we need this information? This is necessary and important information.
Yes, so you're touching on just a few of the angles that you can address with meteor observations. So meteor observations are unique. The meteors are caused by sort of little chunks that are maybe a centimeter or so in size, millimeter, fairly small bits of material. They are created by comets and primitive asteroids. They're from initially a cloud around the comet. They quickly evolve into these streams. Those streams you really cannot detect by any other means than to look at our atmosphere and see those rocks come in. There's not enough dense enough to see it in infrared light, for example. You don't see it in visible light. They're there, and they are important for many reasons. One, of course, is that these relatively large bits move at incredible speeds around the sun, especially relative to the Earth. If a rock comes from far and it hits us from the front, it can hit at 72 kilometers in a second. So in a single second, you move 72 kilometers. If you catch up on the Earth, you still fall into the gravity well of the Earth. That's still 11 kilometers in a second. So yeah, it's astronomical numbers, astronomical speed. So that means that every little rock carries a lot of kinetic energy, and that energy is a little bit of that goes into light, and that's why you see the shooting star, even if it's far away. So these rocks sort of this size are important because when comets formed back in the early days, beginning of solar system, they formed out of pebbles, out of these little chunks. And that is because you can grow dust into bigger material until it gets so big that it's no longer coupled to the gas. So if it can move by itself and not being bothered by the gas, then these rocks will collide with each other and they will break each other apart. And so you never sort of get above this, say 1 centimeter or a few millimeter size. And that's interesting. So how do you then get a comet? Well, the thinking is that there were like these collapses, that a lot of these pebbles suddenly collapsed to make a comet. And so that means that if we look at a comet in the sky, or we look at a meteorite stream, we basically see this object that was formed by the collapse of a cloud of pebbles fall apart again in a cloud of pebbles. And sure enough, that cloud of pebbles tells you about the origin of the solar system, about how comets were formed and what the conditions were in different parts of the solar system. So that's one angle to this. You can learn about how comets evolve. You see basically like a history book, like everything that happens to comets that come close to its orbit in recent, thousands and 10,000 years periods. You can see that written in the form of the streams of meteorites that they leave behind. And they impact the Earth, and that tells us not just where the parent bodies are, and that's the other thing. You can use them as a trail of crumbs to tell you where dangerous comets are. But it tells you the evolution of the object. So what the properties are. You can measure the properties of the meteorites while they're going through its atmosphere. And of course, you get the orbit. You can trace the rock going through the Earth's atmosphere by these cameras. That gives you an orbit in space. And you can use those orbits in space to figure out where things are coming from, not just from comets, but you can also do this with meteorite falls, like, for example, this fall in Novato. So that's sort of what we are, why we are interested in meteors.
Okay, and so on a moment-to-moment basis, this is a screen grab from the SETI CAMS project. This is how long did it take for you guys to record all of those meteorites?
So this is from last night. It's the data are coming in autonomously. They're being processed. The trajectories are being calculated, and each point is the direction from which a meteor approaches us. So you can see the constellations as black lines there. I recognize the square of Pegasus in the top right.
There it is.
Yeah, I see Orion is sort of covered by other meteorites because, of course, the early sort of Orionids are coming our way. You see the Taurids there. They're not in Taurus yet. They're at the moment in Pisces, but that's the blue ones. They will gradually move further towards Taurus in the coming months. Each point is one shooting star, one meteor. But if you take them all together, then you start seeing the meteor showers, and those are those blobs. Those are the concentrations, meteors coming from the same direction. And that's basically what happens when a comet lets go of some dust. The material moves in the orbit of the comet or the asteroid and evolves over time, spreads out, but still has that sort of general motion. And that's what you're seeing here. And I don't know if you can see it at the very top right corner. There are some really dark blue points. That's that new shower. That's the key signet that had its peak yesterday.
So tell us, how do you use this image or a series of images like this to detect an unrecorded, previously undiscovered shower?
So we have we have like a lookup table, like a template that we compare each orbit to and say, okay, this orbit looks like something we've seen in the past. That's why all the Taurids are colored in blue, for example. And the Orionids in red, because we've seen these showers in the past. Those are annual showers. They return annually. Showers that are new would show up as a blob of white points. The white points are basically the sporadics, the unidentified meteors. And if you see a clustering there, that could mean that you have a new meteor shower discovered.
Okay, all right. So what are we hoping that CAMS will do in the next 10 years of this project? It's been going a long time already.
Yeah, exactly. What we have done is map out our annual meteor showers. What we want to do is understand all these irregular showers, like the key cygnets, showers that do not show every year. Some showers, for example, from long period comets, I should add dangerous long period comets, create meteor showers that only show up once or twice every 60 years. So you have to stay at this for some time to really detect all the streams that are out there. And so that's our interest, is to build a better picture of all these meteorite streams that are out there in the space between, outside of Earth.
Okay. Peter, what's the website? People who want to become involved or find out more about CAMS, where do they go?
The website is cams.seti.org.
Okay. And now the image we're looking at is from an interactive tool. And can you give us the URL for that too? I'm going to put all of these in the description
Yeah,
of the video.
sure. This is meteorshowers.seti.org. There's also a website called cams.seti.org/FDL with capital letters. I'll provide that to you. The cool thing about this website is that it not just shows you which meteor showers are active tonight. You can go a year back and look what happened last year on the same date, so you can really see what you would expect to see the coming night. But you can also see how the streams look like in space. So if you click on one of these points, it brings up another website. And that displays the sort of a planetarium program. It's not a computer simulation, it's actually a data visualization of all these points you're seeing here, all the corresponding orbits in the solar system.
Wow. So that's actually a very useful tool that somebody who just wants to go out and watch some shooting stars. They know
Yes.
the big meteor showers coming, and they can just go visit.
And if you
your
see a
website.
shooting star and you track it along the stars, this map tells you which showers are active. So you trace the shooting star back. If it passes one of these clusters, then okay, that's probably the shower that it belonged to.
Wow. So this is not just an important project, it's a very useful one, and it's one that everyday people can become involved in if they feel the spirit move them in that direction. Peter, it was very great talking to you. I really enjoyed that. Great information. Yeah, hold up that book one more time for us so people can. Yeah.
Atlas of Earth's Meteor Showers.
Right. And
this is like your birder's guide to all the meteor showers that exist in the world. It's basically gives for each shower, gives a map and then some information on, what it is, where it came from, who discovered it first, and so on.
Perfect.
Another thing that people can really be engaged in is these fireballs. So there are a lot of fireballs in the sky. We pick them up occasionally with CAMS, but more often not. And we depend on visual observers to report these fireballs. So the American Meteor Society has a website for fireball reporting. Go there, list your observations. It will be tallied with other people in your area that see the same event. And they also use a very rudimentary triangulation of the observations based on visual observations. You saying, I saw it go from there to there. They can use that to give a first indication of where approximately this fireball was. And then we can go into our data and see if we caught it and get a more precise trajectory calculated.
It's fun stuff, isn't it? It's fun to go out and watch those meteors and then be involved in tracking them down later if they're to be found. Okay, Peter, thanks again for being here.
Pleasure.
Hang around backstage, and I will say goodbye to this audience of ours. That's you guys, folks. Thank you so much for being here. As always, give us a like. Don't forget to subscribe. visit us over at earthsky.org. Sign up for our newsletter. We get it out every day. Well, we take one day off a week. And, it tells me I got to go. Anyway, so I'll see you next time. I'm Dave Adalian. One Earth, one sky, EarthSky. Thank you for being here.